In this video, we continue our look at infinite series. We will take a look at the integral test and specifically do an example that actually involves integration by parts. So let's first remind ourselves what the integral test states. The integral test states that suppose we have an infinite series with positive terms, and suppose there exists a function f and a positive integer capital N such that the following three conditions are satisfied. Number 1, f is a continuous function. Number 2, f is decreasing. And number 3, f of n equals a sub n for all integers n greater than or equal to capital N, meaning f is a function that directly corresponds to the terms in the infinite series. If those three conditions are satisfied, then the infinite series n equals 1 to infinity of a sub n and the improper integral capital N to infinity of f of x dx will either both converge or both diverge. To determine the convergence or divergence of an infinite series, all we have to do is look at the corresponding integral of a function that corresponds to those terms. Let's then use the integral test to determine whether the following series converges or diverges. I have the infinite series n equals 1 to infinity of n times e to the negative n over 2. Let's write down that series, and then let's also write a corresponding function for that series. I have n times e to the negative n over 2. So let's look at the corresponding function f of x equals x times e to the negative x over 2. If you like, that's the same thing as x over e to the x over 2. Now, we have to satisfy three things first. First, we have to make sure that our function f is positive. Then we need to make sure that our function f is decreasing. And we need to make sure that our function f is continuous. Well, looking at the function we're starting with, this function is always continuous. In fact, there is no restrictions on the domain. X can be any real number, so this function is continuous. This function is also positive. How do we know it's positive? It's positive because we are looking at all values bigger than 1 for sure, and that means x will be positive. And e to any power is always positive, so positive divided by positive is positive. So f is always positive. Now, how about decreasing? Now, we've mentioned decreasing is a little trickier. To test decreasing, you can draw a graph, or you can take the first derivative. So how about I take the first derivative? The graph isn't quite as clear for me. I would have to pull it up on Desmos, which is easy. I could do that, so we could graph it on Desmos, and then we could decide, is this decreasing? But let's just put our Calculus 1 skills to use. Let's take the first derivative of this function. So if we want to take the first derivative of f of x equals x times e to the negative x over 2, I'm going to apply the product rule. And the product rule says, take the derivative of the first times the second plus the derivative of the second times the first. Let's put this all together. That gives me 1 over e to the x over 2 plus, and over here I have negative x over 2e to the x over 2. And if I go one more step and put this together, that tells me that the derivative of f is just 2 minus x over 2e to the x over 2. Now, to show it's decreasing, what do we want to do with the derivative? To show it's decreasing, we want to show that the derivative is always less than 0. And let's talk. E to any power is always positive. 2 minus x, well, assuming x is some number bigger than 2, so if x is greater than 2, well, that will make 2 minus x a negative number, correct? 2 minus x will be less than 0 as long as x is greater than 2, right? 2 minus some number bigger than 2 is always going to be a negative number. So if the top is actually a negative number for all values bigger than 2, and the bottom is always positive, that means my first derivative will always be negative or less than 0, provided we're bigger than 2. So in this case, 2 is this n value, which as long as we're bigger than 2, our function will be decreasing. That means the three conditions of the integral test are satisfied. And I've mentioned before, sometimes this is the hardest part of the integral test, is actually making sure that those three conditions are met. So now we go ahead and actually take the improper integral. Let's apply the integral test to our infinite series. Remembering that the function is decreasing when x is bigger than 2, we look at the improper integral of 3 to infinity of x e to the negative x over 2 dx. We rewrite that with a limit. That's the limit as b goes to infinity of the integral from 3 to b of x times e to the negative x over 2 dx. This is a product, huh? In fact, this is a classic integration by parts. So we are going to apply the integration by parts formula to evaluate this integral. In integration by parts, we have to select a u and we have to select a dv. For this problem, we'll let u be x and we'll let dv be e to the negative x over 2 dx. Then the derivative of u is just the derivative of x, or 1 dx, and v is the antiderivative of dv, which is going to be negative 2 e to the negative x over 2. Our formula, recall, is uv minus the integral of v du, or ultraviolet voodoo. And so that gives us the limit as b goes to infinity of, here we go, uv. So it's going to be x times negative 2 e to the negative x over 2 minus the integral of v negative 2 e to the negative x over 2 dx, all evaluated from 1 to b. We continue. So this is equal to, let's rewrite the limit as b goes to infinity of, and this is negative 2x over e to the x over 2 plus 2 times the integral of e to the negative x over 2 dx. From 3 to b. Oh, I see I have a mistake in this last one too. So that's from 3 to b, sorry. What does this equal? This is equal to the limit as b goes to infinity, again, of negative 2x over e to the x over 2 minus, and this is going to give us 4 over e to the x over 2 from 3 to b. Let's substitute in our limits. We have the limit as b goes to infinity of negative 2b over e to the b over 2 minus 4 over e to the b over 2 plus 2 times 3 over e to the 3 over 2 plus 4 over e to the 3 over 2. Okay, let's evaluate this limit. Well, b over 2 as the exponent on e, if I have 4 over e to the b over 2, and I let b go to infinity, e to the b over 2 is going to go to infinity and grow infinitely large. So that means this term here goes to 0. What about this first limit with b's? Well, notice if I plug infinity in, I have infinity over infinity, which is a classic example for L'Hopital's rule. So I'm working backwards here, but we're going to apply L'Hopital's rule, which means we're going to take the derivative on the top and the derivative on the bottom. So really, we're going to evaluate the limit as b goes to infinity of the derivative of negative 2b, which is negative 2, over the derivative of e to the b over 2, which is e to the b over 2 times 1/2. What happens to this? Well, as b goes to infinity, you can see that the bottom, again, will grow infinitely large, and so that also goes to 0. So the first term goes to 0, the second term goes to 0, but the last two terms, well, those will converge to a finite number, right? 6 over e to the 3/2 plus 4 over e to the 3/2. So that's really 10 over e to the 3/2. But what's important is that this is a finite number. This is a finite number. And we know that if an improper integral goes to a finite number, what does that tell us about the integral? That tells us that the integral converges. And if the integral converges, then the integral test tells us that the infinite series converges. So let's write down that conclusion. The series converges by the integral test. That was a lot of work. So the integral test is yet another way to help us determine if a series converges or diverges. It does take a long time to do the integral test, especially when you have to do multiple things such as L'Hopital's rule, integration by parts. In addition, we have to check that our function is positive, decreasing, and continuous. One direct consequence of the integral test is something called the p-series test. That one is really useful and very quick to apply. So we're going to take a look at the p-series test in our next video.